All right, so we're going to look at Chapter 7, practice problems from the back of the chapter. And we're going to do 7.1 to 7.3, section 7.1 to 7.3. And I am picking problems that most reflect the types of problems that you'll see on the exam. Okay, so first, this is 7.2. Arrange the following in increasing lambda, which is wavelength. So something to remember is that as wavelength goes up, that means frequency nu goes down and energy also goes down. So as we're ordering these in increasing wavelength, we are also ordering them in decreasing frequency and decreasing energy. The shortest of these wavelengths, or the highest energy, would be X-ray. X-ray would be your shortest wavelength of these 6 options. Then UV. UV is the next most energetic, or the second shortest wavelength. And then I would put visible light. After visible light would come IR, infrared. After IR would be microwave. And last but not least, the longest wavelength of these 6 and the lowest energy would be radio. Okay, next problem is 7.5, and the problem asks you to order each of these waves, so A, B, and C, in increasing frequency, energy, and amplitude. So let's color code these. Let's say for frequency, we're going to use red. For energy, we're going to use blue. And amplitude, we're going to use green. So let's start with amplitude. So amplitude is the height of the wave. So I see where the wave starts and how far it is to the peak, where the wave starts and how far it is to the peak, where the wave starts and how far it is to the peak. So in the book it's drawn a little bit differently, but here it looks like A and C have relatively equal amplitudes. Maybe A looks a little higher. So just refer to your book because they're drawn a little bit differently. So I'm going to say for sure B is the shortest. Then probably C is the next highest. And then A is the highest amplitude. The peak goes up the highest. Now let's do energy. So remember, like we put in the previous problem, as frequency goes down, energy goes down, and as wavelength goes up, energy goes down. So really, in order to know the least energetic wave, or to determine the least energetic wave, I need to determine the longest wavelength. Okay, so wavelength, again, is going to be from the top of my wave, the distance from the top to the top. Okay, so this right here is my wavelength. Or we can go from start here to finish. So from start to finish, when it goes up, down, and meets back at its initial position. Here I'm going to go start, or peak to peak. So looking at each of these, I think this is my longest wavelength. This is probably my second longest. And I would say this is my shortest. So this means this is my highest energy, This is my second highest energy, and this is my lowest energy. So if I'm ordering them and increasing energies, then I would start with C, I would go to B, and then I would go A. Okay, last is frequency. Frequency is the same trend as energy, so I'm just going to copy what I just put, C, B, and A. It's most easiest to look at wavelength and determine energy and frequency from the wavelength. Okay, this next one is 7.8. It says FM station broadcast music at 93.5 megahertz. Find the wavelength in nanometers of these waves. So this, and I neglected to give a difficulty score to each of the previous problems, so I'll tell you that now. The first problem, I'm going to scroll down to it. The first problem, 7.2, I would have given a 1. The second problem, I would have also given a 1. And this problem, I also believe, is a 1. Okay, so these are the easiest types of problems that you'll see on the exam. Because this is an equation that you should be familiar with, you should know that the speed of light is equal to the wavelength times the frequency. Okay, you will see frequency both as nu or as this cursive F. Okay, so both refer to frequency. You should know at this point that C equals 3.00 times 10 to the 8 meters per second. And you should know that a hertz given in the problem refers to a frequency measurement. So I know nu is equal to 93.5 megahertz. Okay, because I want nanometers, that means I am solving, it says find the wavelength in nanometers. That means I'm solving, right, for lambda. Okay, so I am plugging in the speed of light constant, and then I'm also plugging in the frequency that was given to me. I need to make sure the units match though. So notice that because the speed of light is in meters per second, and because a hertz equals second to the -1, I need to make sure to convert megahertz into hertz. All right? So I'm going to take this value. I'm going to say for every hertz, however many megahertz there are. Mega is 10 to the 6, so I know because hertz is a smaller measurement than mega, mega is big, I need more of them per 1 megahertz, so I have 10 to the 6 on top. So this is going to give me 9.35 times 10 to the 7 hertz. Now I'm going to take that value and plug it into my original equation. I'll do that in green. So 3.00 times 10 to the 8 meters per second is equal to lambda, which I'm solving for, times 9.35 times 10 to the 7 hertz. Awesome. So if I divide by 9.35 times 10 to the 7 hertz on each side, I will get lambda by itself. 7 hertz. You should get a value for lambda of 3.209 meters, because this hertz cancels out with this seconds, because this hertz, remember again, is second to the -1, which puts it on the numerator, which cancels it out with this second that's on the denominator. So I'm left with meters by itself. And the question asks for nanometers, so you're going to have to take 3.209. I believe we have 3 sig figs, meters. And since I want it in nanometers, I know for every 1 meter, since nano is a smaller measurement, there's 10 to the 9th nanometers for every 1 meter. So this will get you 3.21 times 10 to the 9th nanometer is the wavelength of that radiation and through which the FM station broadcasts. Okay, let's look at 7.14. So this says, let's see if I can move this whole thing. So it says covalent bonds absorb infrared and vibrate. Part A says, and we're just going to look at part A, a carbon-oxygen bond absorbs 9.6 micrometer wave radiation. What is the corresponding frequency in hertz? Okay, so again, this is utilizing the equation C equals lambda times nu, or C equals lambda times frequency. So I'm going to plug in my known values. C I know is 3.00 times 10 to the 8th meters per second, and that is equal to my wavelength. I'm going to put it down here because it is not in the same units as I have in my speed of light, so I need to convert them. So I have 9.6 micrometers. That's going to be my lambda times frequency. And I don't know what frequency is, that's what I'm solving for. So down here, I'm going to convert into meters because I know that the speed of light is in meters per second. So for every 1 meter, I have 10 to the 6th micrometers. So that's going to give me 9.6 times 10 to the negative 6 meters. Because micrometers are going to cancel out, I'm going to take this value, plug it in here, 9.6 times 10 to the negative 6 meters. If I divide it over, I can isolate frequency by itself. You should get a frequency that is equal to 3.1 times 10 to the 13 hertz, because remember, a hertz is equal to a second to the negative 1, or known as per second. Okay, so now let's look at number 24. Okay, for problem 24, there's a couple of different ways to approach this. The problem says, what is the wavelength of photon absorbed when an electron in a hydrogen atom undergoes a transition from N1 to N3? So let's take a minute to actually see what's going on. So remember, the Bohr model of the atom shows orbits that when electrons are in them, they're said to be stationary states, so that they don't emit or radiate energy when they're in these stationary states. So remember, the hydrogen atom only has 1 electron. So we're looking at the transition from n equals 1, which is the lowest energy state, and where the electron has the greatest negative energy, meaning it has the lowest energy, and it's going to go up to n equals 3. N equals 3. Notice the gap in energy is larger from 1 to 2, then from 2 to 3, then from 3 to 4. So the difference in energy from one level to another level gets increasingly smaller. So the biggest jump in energy is going to be from 1 to 2, and then from 2 to 3. So we have a large amount of energy that's being absorbed. The wavelength of that photon corresponds to a lot of energy because the electron is going from n equal 1, the lowest energy the electron has, to now n equals 3. Okay, so you can use either the Rydberg equation, or you can use apply Bohr's equation for the energy level of an atom, which is on page 297 of your text. We're going to use that one since you haven't seen it yet, but it's very similar to the Rydberg equation. Okay, so I'm going to write this out for you. This says that the change in energy of an electronic transition, so the amount of energy change for that electron, is equal to the final, E final minus E initial, which just means negative 2.18 times 10 to the negative 18 joules times the electronic transition, which is 1 over N final squared minus 1 over N initial squared. Okay, so since this question says that the electron transitioned from n equals 1 to n equals 3, my final is going to be 3, and I'll square it. My initial is where it came from, so that's n equals 1 squared. This is going to give me the energy change of the electron, and it's also going to give me the energy of the photon that was absorbed. I'm going to apply negative 2.18 times 10 to the negative 18 joules. This gives me negative 2.18 times 10 to the negative 18 joules times 1 over 9 minus 1 over 1, which is just 1. This will then give you 1.9378 times 10 to the negative 18 joules, because what was in the parentheses had no units. Okay, this corresponds to the energy change of the electronic transition, or it corresponds to the energy of photon absorbed. I can take that along with my equation. I move this over to the side just so we'd have more room. Energy of a photon is equal to Planck's constant times speed of light over lambda. I can get lambda by itself, so lambda is equal to hc over E. If I plug everything in, I would get 6.626 times 10 to the negative 34 joules seconds times 3.00 times 10 to the 8 meters per second over the energy that we just solved for, which is 9378 times 10 to the negative 18. So let's look at what cancels out. Oops, I forgot my units. These are joules. So what cancels out is joules and then seconds. So we're just left with meters. I'm going to put my answer up here. Your wavelength that you should get after this calculation is 103 nanometers. I converted to nanometers. So remember that for every 1 meter, there are 10 to the 9th nanometers. So I did that conversion on my own, but this would be your final answer. The energy states that are given, 1 and 3, will not dictate or limit the amount of significant figures in your answer. Okay. Now let's go to 40. Now I neglected to tell you that what I would rate each of these problems. So the problem prior, number 14, problem 714, I would still give a 1. It's a very simple problem, so that's number 14. Number 24, I would probably give a 2 or 3, so I would give this a number 2 or 3. And this upcoming problem number 40, I would give a 3. So this is going to be given a difficulty rating of a 3. Okay, so let's look at this problem. We haven't gone over this in class. An alpha particle that has this mass is emitted by radium isotope. Let's move this over so you can see it a little bit more. Is emitted by a radium isotope. Great. It travels at 3.4 times 10 to the 7 plus or minus 0.1 times 10 to the 7 miles per hour. The reason that this problem is a little bit more difficult, I think, than number 24 is because there are a lot of conversions that are necessary to be made in this problem. So let's first look at problem 40, part A. So according to de Broglie, all matter behaves also as a wave, but the larger the mass, the smaller and the more undetectable the wavelength is. So we're going to set up our equation for part A. I know that the wavelength, de Broglie wavelength, is equal to Planck's constant divided by the mass of the object that I'm studying times the speed of that object. Okay, so writing this out, I have 6.626 times 10 to the negative 34. I'm going to write out what a joule is, and you should be familiar with this so you know how units cancel. A joule is a kilogram meter squared per second squared, and then we have times second, so times second, over the mass, which is 6.6 times 10 to the, now wait just a second, it's given in grams, so I have to convert that to kilograms since my joule is a kilogram meter second per second squared. So this should be times 10 to the negative 27th kilograms times the speed is given as 3.4 times 10 to the 7th. So notice that's in miles per hour. I would like to get that in meters and seconds. So let's do that conversion down here. 3.4 times 10 to the 7th miles, and we'll get into the uncertainty, this plus or minus, when we get into part B, miles per hour. I know for every 1 hour, there are 3,600 seconds. Pull this up. And then for every 1 mile, there are 1609 meters. Just make sure to pay attention to the study guide. It'll tell you which conversions to memorize, but most of the conversions I will give you on the exam. So hours will cancel, miles will cancel, and that should give you 1.52 times 10 to the 7th meters per second. So I'm going to plug that in here. 1.52 times 10 to the 7th meters per second. And then let's look at the units that cancel. Kilograms cancel. This second cancels out with that squared. Meters cancel out with this top squared meter. Seconds with seconds, so we're left with a meter by itself. And that should give you 6.6 times 10 to the negative 15 meters for the wavelength. Okay, great. So notice that's a rather small wavelength. For something that is more massive, it has a smaller, more undetectable wavelength. Okay, let's look at part B. I like changing my colors. So part B says, what is the uncertainty in position? So that brings into discussion Heisenberg uncertainty principle. So I'm going to write that, our equation for Heisenberg uncertainty principle here. Heisenberg uncertainty principle says the uncertainty in position, that's what delta x is, times the mass times the uncertainty in speed, which really that is the uncertainty in momentum. But specifically here we're looking at speed and mass, is greater than or equal to a constant, which is Planck's constant, over 4 times pi. So we want to solve for the uncertainty in position in this case. So what we need to first calculate is this. We want the mass times the uncertainty in position, or sorry, uncertainty in speed. So I'm going to bring this up. Notice that in the problem it says that the speed is 3.4 times 10 to the 7th plus or minus 0.1 times 10 to the 7th miles per hour. So that is essentially what your uncertainty in speed is. So in order to calculate delta x, I have to plug in all these other values, which is my mass. So I'm going to do 6.6 times 10 to the negative, keep it in kilograms, 27 kilograms, times the uncertainty in speed. I'm going to use the value of meters per second though. I need meters per second here because over here, remember Planck's constant is joules times second, and there's a meter and a second in Planck's constant, so I need to take my uncertainty, which is 0.1 times 10 to the negative 7 miles per hour. I'm going to convert 1 hour, 3,600 seconds, 1609 meters per 1 mile. That should give you 4.47 times 10 to the negative 9 meters per second. Miles cancel, hours cancel, left with meters per second. Great, so now I'm going to take this number and plug it in here. I know that's greater than or equal to, so I'm going to set this equal to Planck's constant joules times second over 4 pi. So if I divide this over here, then I can get delta x, or the uncertainty position, by itself. Okay, so when I set this up, I have the following. I expanded what a joule is. So I have kilograms, meter second per second squared times second over 4 pi times, this is the mass, times the uncertainty in the speed. So I'm going to correct something here though, the significant figure. So really the line should be here, because remember in the question here, it gives you the speed in 3.4 times 10 to the 7th plus or minus 0.1. So this is plus or minus that decimal place, and overall this is 2 decimal places. So really I want to go to the first decimal place when I take that value. So I should have 2 significant figures there. So let's pull this whole thing up, and let's look at how the units end up canceling each other out. So kilograms cancel out with kilograms here. Second crosses off that squared, so I just have 1 second left. Then I cross this second out with this second, so now I no longer have seconds. And this meters cancels out with the squared meter, so I end up with just meters by itself. When you compute this value, you should get 1.8 meters. And this would be your uncertainty in position, or your delta x. Okay, so I would rate this problem, A, I already rated, but B, I would rate a 4. This would be a 4 in terms of difficulty, because there's a lot of steps, and it's really easy to miss a step or to miss a conversion. And you also have to understand what each component of the problem means. So this would be a number 4 in terms of difficulty. Okay, so what I want to do before I close out this video is show you a couple of other things that you should be able to do. Although the questions that I picked don't specifically ask for them, there are other questions that will come on the exam, which are similar to how I'm going to manipulate these problems. So let's scroll back to number 24. So remember in 24, it asks for the wavelength of a photon that was absorbed. So I could have just as easily given you the wavelength of the photon and then asked you what transition that corresponds to. So for instance, I could say that the electron started at n equals 1, and I need you to solve for n equals the final position. So I need you to tell me, well, where did the electron end up? So let's see if we can do that. We're going to take number 24, and we're going to solve for the final position of the electron. N equals 5. So the n final equals what? That's what we're solving for. Okay, so I'm going to take this problem and write it down at the bottom. So the question could be something like this. If a photon of 103 nanometers is absorbed by an H atom, or a hydrogen atom, in a relaxed state, to what excited state did the electron jump? So there's several pieces of information given in this problem. One is the wavelength of light that was absorbed. The other is that the hydrogen atom is in a relaxed state. You should know that this means that the electron is at n equals 1. 1 is the relaxed state, the most relaxed state of the hydrogen atom when the electron is at n equals 1. To what excited state did the electron jump? So that's telling you that you're solving for n final. I want to know what n final is. Okay, so we know several equations actually, so there's various ways that you can approach this problem. So I'm just going to write down everything we know, and these equations will be given to you on the exam. Remember, there's many different paths that you can approach a problem, that you can solve a problem. These are not state functions, meaning they are not path dependent. Okay, so you can choose the path of your choice in solving for these problems as long as it's appropriate. I know the energy of a photon is equal to Planck's constant times the speed of light over the wavelength of that light. I also know the change in energy of an electronic transition is equal to negative 2.18 times 10 to the negative 18 joules multiplied by 1 over n final squared minus 1 over n initial squared. I also know the Heisenberg equation, which says that 1 over wavelength is equal to the Heisenberg constant r times 1 over n1 squared minus 1 over n2 squared. And in this case, n2 is greater than n1. Okay, so because the wavelength is given to me, I can either put the wavelength into this equation for the energy of the photon, or I can put it into this equation. Okay, so I am going to say that we'll use the Heisenberg equation because it's a one-step process, and we'll see what we get from there and see if it matches what we have. Okay, so 1 over, now remember the Heisenberg constant is 1.097 times 10 to the 7 per meter. Okay, since this is in units of meters, I need my wavelength to also be in meters. So I'm going to say that my wavelength is 1.03 times 10 to the negative 7 meters. So I did a quick conversion in my head, but you might need to write that out, is equal to the Heisenberg constant, 1.097 times 10 to the 7 per meter times 1 over, now I know that N2 is greater than N1, since the electron started at n equals 1, that's the lowest possible N value quantum number that I can have. So I'm going to assign N1 as 1, square that, minus 1 over N2 squared. Okay, so the easiest thing to do in this situation is to divide by the constant so that I have this value by itself. I isolate what's in the parentheses on the right side of the equation. So I'm going to divide by r. I'm just going to say divide by r because meters is on the bottom here. When I divide by it on this side, it becomes the numerator. So meters and meters cancel out. So that will show you that the answer to your problem is unitless, which makes sense because quantum numbers are they're integers that have no units. It tells you what energy state the electron is currently positioned. Okay, so if I divide these two numbers, or if I divide 1 over the wavelength, and then I divide that by r, I should get a value of 0.8850. I think we want 3 sig figs, and that is without a unit. I know that's going to be equal to 1 over 1 squared minus 1 over n2 squared. Okay, so I'm going to subtract 1 over 1 squared, which really is just 1. Subtracting 1, that'll give me negative 1 over n2 squared is equal to negative 0.115. I can multiply n over, so times n2 squared times n2 squared. Then I can divide by negative 0.115, divide by negative 0.115. Notice that cancels the negative out. Let's pull this up. Okay, if I compute that value on the left-hand side, I should have 8.6957 is equal to n2 squared. To get n by itself, I need a square root. So you would have n is equal to, we'll say about equal to 2.0 0.95. Because I know n has to be a whole number, I round it to 3. So remember, in the problem that I pulled this from, the electron transition from n equals 1 to n equals 3, so this is checking your work. Now, if I were to give you a problem with this phrasing as opposed to the original phrasing, this would be a number 4 in terms of difficulty. It is a lot more difficult to go in this direction because there's a lot more math involved. So when you're doing these problems, switch the variables. Don't get comfortable with just solving for one type of variable. Solve for n1, solve for n2, solve for energy, solve for mass, solve for momentum when it comes to the Heisenberg uncertainty principle. Don't get comfortable with one type of variable that you're solving for. And make sure that you're aware that there can be different wording. I won't just give you numbers. I can say if hydrogen is in a relaxed state, you should know that that means n equals 1. The electron is at n equals 1. If I say that the emission of the photon emission corresponds to a Lyman series, you should know that that means that the electron is going from an excited state to n equals 1. If I say the Balmer series, you should know that the electron is excited to somewhere above n equals 2 and then it relaxes to n equals 2. So you need to be comfortable with all types of wording. And make sure you also are aware that if I'm looking at these stationary states, these orbits, that you know if an electron is going up, that it's absorbing a photon. This is absorbing a photon. If an electron is going down, it's emitting a photon. Something you want to visually be comfortable with. Okay, good luck. Practice all the problems you can. Okay, there is a correction to problem 40, part B. In the problem above, I mistakenly put -7 as the exponent for the uncertainty associated with speed. It should have been a +7. I just made an error in writing the number down. So your final answer, after you correct that exponent and get the uncertainty of speed in meters per second and plug that into the equation from part 40, then your final answer would be 1.8 times 10 to the -14 meters, not 1.8 meters. So make sure that you fix that for problem 40, part B.